Okay, yeah, thank you. So yeah, I will continue. So last time we stopped at the theorem. So even I want to present at the, I mean, so this time, but anyway, so we have given such a theorem, right? So let G be locally compact host of Etel groupoids. Okay. Somewhat setting, which is minimal. Of course, okay, minimal. Almost elementary. Of course, so we should add here. So the unit space is compact. Okay, so and this guy implying that the groupoid is topological, pretty simple. Yeah. So suppose you have such a properties. So then your C star reduce the C algebra of this guy is unital, simple, trivially Z stable. Yeah, so you have such a theorem. So and we have given several pictures, but I didn't give any formal definitions of this guy, right? So maybe today we start with this definition. Okay, so recall what is elementary groupoid. So so I need to check it. So this definition appears in the Reynolds book. So yeah, they call it elementary groupoid. So so the H, no, let me write in this way. So let us see be a bunch of the bisections. Maybe the C, IJ, L, such that the maybe your IJ comes from some the IL and your L comes from another index at F. Okay, so this is a the set of bisections. Such that the following holds. Okay, so first one, so your Cij L and times Cjkl. So exactly your Cikl. So you have the transitivity here. And the second, so your Ciil are just a set, okay, of the I mean the subset of the unit space, and such that your yeah, sure. So here we want to open, so open bisections. So this guy is a disjoint. Okay. Of course, so you need the Zij L inverse is exactly your Zj Il. Okay. So you have this one, and then the third one is that so if you have different L, so actually your towers are disjoint. Okay, so you have the Cij L times your Ci B prime J prime L prime, okay, equal empty. If your L is not equal L prime. So okay, so this side will give us the picture that I was drawing last time. So you have okay, so this is maybe your C11, okay, L C22L, okay. So you have this is correspond to the maybe the one multi-section here. So and the like the C the errors from the C11L to the C22L, it's just exactly the. So it's like a tube, right? So you have this one, and then you have the other L. Okay, so maybe so this is the C11 L prime, so C22 L prime, and you have a lot of this, right? So, and in this case, we have a bunch of towers, and we call this a, this collection of towers a castle. Okay, and note that so there's no arrows between towers. Okay, all arrows just the all allowed arrows are just the vertical arrows. Okay, there's no horizontal arrows. So in this case, if you just take the union of all such bisections, so you obtain a groupoid. Okay. So the H C, you take the unit, so like the L in F and your I in IL. Okay. No, IJ in L, so also IJL. So it's a groupoid, and it's called the so-called elementary groupoid. It's called elementary groupoid. Yeah. So then what is a groupoid? Okay. So what does the almost elementary mean? Okay. So actually that means somehow it can be approximated by elementary groupoid. So in some certain sense. Okay. So a groupoid G is said to be almost elementary. If okay, so for any compact set K in G, and so for any open cover V of G0, know that. So here we assume that G0 is just a compact, not locally compact. Okay. And open set O, okay, also contained in G0. Okay, we can always find okay there exists so two open castles. C and D. Okay, so C and D are just of this form, right? So it consists a lot of the bisections, such that the first one is we call it the extendability by K. So you are K times HC is contained in HD. So what does this mean? This means okay, you can look at this picture. Okay, we go back to this. Okay, so beyond C, okay, beyond C, even you can just take the C is a part of the D. It doesn't matter. So you have some extra open side, okay, in the G0, and you want your K. Okay, it's a given. It's it's given at the very beginning, right? So the you consider the errors. Okay, so this is one error containing C, and you want to times K here. So K is just some compact set. This means you compose some errors in K. But finally, you will find that so the errors you obtain after the composition is still contained in the D. That's the point. So that's extendability. So the reason we introduced this is because this somehow it's just like so you can approximate the partial dynamics implemented by K by using two towers. Okay, so that everything will behave very good. and you will obtain a very good finite dimensional approximation so that you will obtain the tracial stability. Okay, I will explain so the later. So a little bit, I mean, on the idea of the proof. Second, okay, we also need the diameter. Of course, sorry, so maybe I forget one condition. So definitely you want it to be separable, right? So you need to add the this guy is a compound metrodable. And actually, so because it's locally compact Hausdorff, so and your G0 is metrodable and your groupoid is etal. So then this will tell you that your groupoid is indeed second count. Okay, anyway, so then what we want is that okay, we can do not use the diameter here. So any for each level, so maybe a DIIL, okay, contained in D, right? There exists V in V such that your DIIL is contained in V. So somehow it means the diameter of the levels of the castle D. I mean, usually it contains C. So because if you choose your K containing the unit space, so this by this one, so HC is containing HD. So that actually means so all levels in D and in C can be uniformly small. The third one, okay, that means the remainder of the all maybe your L in I and the I in IL in F, okay, CIIL. So that means you just consider remainder of the C castle. It can be dynamically small. So I will not say too much about this. You just to think that it is quite small. Okay, then the given set, given open set O. So this is called dynamical small. And if your groupoid is ample, that means if you just consider like the zero-dimensional setting, so you can just erase this by somehow consider like oh no, I don't think yeah, actually, so if your groupoid is ample, you just replace this one by the unit space is partitioned by D. Okay, you can do this. Okay, so then some examples. Yeah. So so the Jiangsu algebra Z has what? Oh, sorry, not should be the unit space. So examples. So the Jiangsu algebra has almost elementary groupoid model. So and the RAF algebras has almost elementary groupoid model, and even so all UCT Kirchberg algebra unital, I should say. So all of them have the almost elementary groupoid model. So so we just try to verify our conditions in, I mean, on the groupoid, so discovered in the literature and finance. So
but just to clarify, by hand, do you mean did you have to build a one that was different from the ones that existed already? For example, for Z, my understanding there's a paper by Karen Strong and some other people,
yeah,
which has like built it from these minimal
partial dynamical system.
Of spheres, right? Of the
Yeah, but
one-dimensional spheres. So does that one?
yeah, exactly the other one. So you just somehow you eliminate 1 point from the sphere, and then you consider the partial dynamical systems induced by this. I mean, by this dynamical system, but you eliminate 1 point. Okay, so that partial dynamical systems will give you the groupoid model of Z, and recently we verified that. So this that groupoid is so satisfied almost elementariness. And for other ones, for AF algebra is I mean, it's much more it's much more easier to see, because for I should say unitary, because unitary AF algebra comes from the AF groupoid, but the AF groupoid is you can very easily to verify that. So yeah, they are almost elementary. Okay, and so UCT unitary crystal algebra, so have groupoid model comes from like the hybrid graph groupoid. So and you just verify conditions there. But I should say, so in this case, what we have shown is that so the pure infiniteness in some sense, I mean, for groupoid, is equivalent to the almost elementariness, and we verify the pure infiniteness for groupoid for such a groupoid for UCT unitary crystal algebras. Okay. So so that's an example. So because the last time, so people are interested in how to show the theorem. Theorem. So maybe I cannot see all details because it is quite long and complicated, but I can see some ideas here. So what we use is the threshold stability, okay, discovered by the Horowitz and Hirschberg, right? So okay, maybe theorem or even the definition by Horowitz. No, Hirschberg should be. So A is I mean, of course, you need unitary simple somehow I mean standard definition. No assumption for A. So A is trivially is stable. A may not be nuclear. So trivially is stable if the following happens. Okay, if for any n and any A in the positive part of the A, you can find a CPC map. Okay, y from the n of C to your A, right? Such that your one A minus the phi of the one n, okay, is smaller than your A, and of course, so you also need a finite set omega, right, in A, and also just 1 second. So for any B in omega and any like the X in the MNC of norm 1. Okay. So one has it is almost, I mean, the B and the phi and X, okay, it's almost commutative, okay, by controlled by this epsilon. Okay. Okay, so that's a threshold stability. Yes.
If you want the map to be all together, fine.
Oh yeah, sure. Sorry. Yes. Okay. So we just use these conditions to construct such CPC order 0 map to satisfy these two conditions. Yeah. Okay, how to do this? and go back here. So we actually use our definition. I mean, you need to do some works to obtain a nesting castles. Okay, what do I mean? Nesting is you have a causal castle. The levels are big in a topological sense. So this maybe you are C. Okay, and then you have a finer castle. Okay, nesting inside. Okay, you have some castles here. So the blue one and the red, the blue one and the red one side comes from the one castle. Okay, one castle. So, but I want to separate them, to partition them into two parts, because I want to give an example to construct how to map the two-dimensional matrix, okay, into our groupoids algebra. So we need to separate them into two parts. Now, of course, you do the same work here, right? So then what I want is to then, because they're castles, so you can consider the errors, okay, between the red ones and the blue ones. Okay. And just let's say, so they are like the D, I, J somehow. And then, so I want to construct a map from the M2 C go to the CBC order 0 map. I want to construct such a map from the two-dimensional matrix to this algebra. What I really want to do is to define for ij just equal some sum. Okay, I just you can consider. Okay, let's make our life even more simple. So let's consider the zero-dimensional side. So they are all Klopen levels, or even the Klopen bisections. So I want to add some Dij here. All possible errors from the Di phi, yeah, J to I. Yeah. So I mean, I just consider the bisections, right, from the J to the I, and I just add all indicating functions, okay, supporting on these bisections, and the times some maybe some coefficients here. Okay, so we will see later. So why the coefficients here is important, so that we will get the almost commutativity conditions. But anyway, so our order 0 map, okay, is of this form. Okay, and then why we use this? How can we use this? It's the following way.
So a single Eij you send to just one characteristic function, right? Not to a sum, right? Because you wrote phi of E.
No, I add all possible.
Then I don't quite understand.
So because there are too many Dij here.
Yeah, but a single. So if when you're mapping M2, so you need to map four elements.
Yeah.
So where do you map the?
So that's why I partition them into two colors.
Oh, I see. Okay, no, okay. But.
Yeah, maybe that's not yeah, maybe that's not a good notation, but because there will be too many index here, so it's just like maybe your J now is blue and I is a red.
Okay, now I understand about the,
Yeah.
but you're not. It's just you're not summing over I and J.
Yeah, you're right. Yeah. That's another good. Yeah.
You're not summing over I and J. You're
Yeah.
summing over the castle.
Yeah.
Over the right of the
Yeah.
And what do you do with the positive element in your algebra?
Yeah. So what I will explain. Yeah. So now let's be more formal. So let omega be a finite set in your reduced groupoid system algebra, and your A is positive. Maybe let's define it to be A. A positive. Okay. But by some approximation, very standard approximation property, you can just assume your omega is just some functions supported on some open bisections. Okay. So maybe U1 until UN, such that the closure of the each UI is compound. So that means your open bisections U1 to UN is a pre-compound. Okay. And the A you can also find because one can find a bisection. Maybe open bisection or open set. Okay. Open O in a unit space. Okay, and function supported on O. Okay, F is cons sub-equivalent to A. Okay, you can always assume actually your A is just a function, a positive function. Okay, supported on some open side. Okay, in the G0, and therefore we just use this open set. Okay, instead of this general positive element in A. Okay, and now so let our K is exactly union all possible UI closure. Okay, from 1 to n. And then you do the extension. Okay, what I mean is you find two castles and such that these two hosts. But of course, you need to do some more work to make everything works compatible, such that so I just repeated this picture. Yeah, so you are maybe so this is maybe this two we just for example is your U1. Okay, for example is your one, and this is your C castle here, such that so if you do the extension, so this this C levels. So what I mean is levels contained in the C castle, this coarser castle. By extension, let's go to some of the D castle by using the U1. What I'm using is this part. So, however, so you need to make your D castle works compatible with this picture. So this is some D levels, right? And you have some. Because I once used the blue and the red, now I still use the blue and the red. And this is the red. So know that so there should be a lot of the blue levels and a lot of the red levels also, but I just draw two here. So the D castles in this part by the extendability, it works very well with our K, but in particular for our U1 at this moment. So then what we have is this extendability. right? And this one. Okay. And what is your phi? Your phi maps this to this and this to this. Okay. And now because we are working in castles, okay, which are actually the principal groupoid. So that means, so if you start here and you want to go here, I suppose. So it is equivalent to you go here, then here, equivalent to you go this part, you go, I mean, the horizontal first, and then go vertical, or you go vertical, then go horizontal. That's equivalent, because everything is, I mean, we work in a principal groupoid. Yeah, okay. Now, what is this vertical tube? So it's just phi, maybe EIJ, right? The vertical tubes are just the I mean the part of phi EIJ. And if you go first, that means you times your F UI. Maybe Fi, because I just choose where's my citing? Oh yeah, I use FUI. Okay. This is you go first vertical, then go you go for vertical first, then horizontal next. And what is how about another path? So you go horizontal first, and the vertical, then you have the phi EIJ, the FUI in the front, right? Because you calculate everything from the right to left. So then, if you give a good coefficients here, and we know that, so topological dynamical, I mean topological dynamics in the dynamical setting, in this topological dynamical setting. So you go this, then this, and it's equivalent to you go this first, then next to this. So minus this one. It's quite small. If you put some the good coefficients here. So this give us the commutativity of this part. Of course, you need to do some other works, but this is the essential idea. Okay. And then, because we want the remainder of the C castle is very small. Okay, compared to some O. Okay, and O now is just exactly the support of the function f, which is less than any given positive general elements. So then, by using this, we can verify that. So you are one C. It's actually the indicator function of the unit space minus your phi 1, 2 is less const less than a, const less than a, and this has verified the threshold stability. So I should say, so this is a very rough idea. So, but essentially this is exactly what we do. So the essential idea is this picture. Okay, so anyway, yeah.
Could you explain a little bit? So at least I'm not sure I fully understand why you needed the other capital C. So right, so you use the castle, you only use the castle D to build the map, right?
Yes.
And so where did you use the castle C that you could extend it to D?
Because so this is your castle C, okay?
The large circle.
Yeah, but yeah, sorry. Actually, so this is when you extend it.
The circles are the UIs, right?
What?
The large circle.
Oh yeah, yeah, you're right. So this is a C,
this is,
and you do the extension for the first time to some C prime. And this is your D, and you do extension to some B prime. So actually, there are 4 castles here.
that doesn't help. It makes it worse.
So C extend to some C prime, and the D extend to some D prime. Yeah, to make the array seeing this picture work.
But both of the two sets of castles are coming from the same compact set, or no? I don't understand.
So you can use the same compact set, especially, I mean, in this case, this guy to do extension. But you need to be careful, and you need to do some other preparation to make this work in this way. You have to do some, I mean, to eliminate some levels, somehow like this. So yeah, I said, so this is just a very rough idea. So there are a lot of preparation work need to be done.
So why do you need why do you need like condition one? Like, so, right, because you only use one castle to build a map, right? The open sets just come from the positive element that you selected, right? So where do you need the second castle? Like, where I think I missed where it came into play.
Because no, actually, so you need to use the whole D prime, so the castle after extension to define your phi.
But I thought where do you get, like, for example, for NM2? So do you have to kind of like
yeah,
for a larger n, will you have picked n pairs of castles, or?
Yeah, for MN, you need to divide the final castle into n parts. Yeah.
Okay. And then you use to build that map, but in this map, the way you've written it down, you only use one castle. No.
Yes, but actually, yeah, I should say so. Yeah, I didn't make very clear here. So the picture here is just like the C prime and D prime in this picture.
No, you made that clear. You drew the pictures, but you didn't explain it in the formula. Right? In the formula, you're just adding up the characteristic functions of one of the castles. No?
Yes. When you define your phi, you use only one castle.
Only one castle. And then so do you need the second castle to control the coefficients, or like where does the
Yes, exactly. Yeah, yes. You need the coefficients here.
Are controlled by the
Yeah, by the Causar castle.
All right, that explains it. Thank you.
Yeah. Any questions? I should say it's complicated. I try my best. Okay, so then as I said, so we have a lot of examples of this, but of course, so the stability of that CC algebras I know, but what we want is to show that so our notion is quite generic. Okay. It's not so technical. By the way, so another interesting connection is our notion with the so-called almost finiteness defined by Matsui and then refined by Kerr. So what does Matsui? What is Matsui's almost finite? So almost finiteness. Is that okay? So for any epsilon, and of course, so this works for only for ample group. For any epsilon bigger than 0, and for any compact set, okay, in G, so you can there exists open or compact open elementary groupoid. H, okay, subgroupoid contained in G with, so actually, so as you can see here, so this is elementary groupoid, so you have a castle decomposition for H, and he wants this decomposition actually give you a partition of the unit space. And the most important here is that he wants some Foner condition here. So for any U in the unit, then you consider this the first you consider the orbit in this subgroupoid is then translated by your given K, and you do not want this add too many extra elements compared to your original part, orbit of U in H. Okay, this guy over this guy is less than epsilon for any U in H0. Actually, he needs to be G0. Okay, so this is a matrix condition, and so David Kerr, so he generalized this condition to the higher dimensional case, but in a dynamical system setting. And he showed that, so in a dynamical system setting, so the almost finiteness implying your cross product is Z stable, because so you're in the dynamical system setting, so almost finiteness implies that your acting group is minimal. So your algebra is nuclear automatically. And so you don't have to care about the trivial Z stability, a difference between the trivial Z stability or Z stability. So, but the question is, first question. So after the Kerr's theorem, so whether the original almost finiteness in the groupoid setting also implies that the groupoid is trivial Z stable or Z stable, because at that time, so nobody knows whether the almost finite groupoid implies that your groupoid is a topological amenable. But then people find the counterexamples. So actually, so the right question should be asked that. So does this guy is a trivial Z stable? If your G is almost finite, okay, in matrix sense. So that's the original question. And actually, so this is our the motivation for our work. We then show that of course, so you always need a minimum, otherwise you cannot do anything. Okay. So the theorem also by me and Jian Chao. So we show that, so if the G is a minimal, so G is almost elementary, if and only if. So G is AF, so it's almost finite, if and only if G is almost elementary plus the G is fiber-wise amenable. So this corresponding to the matrix Foner condition here. So I should say, so this is a new amenability for groupoid. So somehow I don't plan to give the definition because it's another framework. But anyway, so that's just means you each source fiber, you treat them as a metric space. Okay, in metric space, then you can define amenability. You can discuss and define amenability for metric space. So that's it. So okay, so fiber-wise amenable. And therefore, so by using this theorem, so actually, so this is true. So by we even do not need this one, so we use extendability instead of this stuff. Okay. Another interesting part is that, so almost finiteness at the beginning, so the motivation to introduce this one is to study a topological full group instead of the CC algebras. But of course, also the matrix motivation is to relate the topological full group to the case theory of the reduced group with CC algebra via the homology of the groupoid. So, but then, so we found that, so actually, so such a notion is related to the classification program of the CC algebras. Okay, and also, so as I mentioned before, so by the example part, so if your groupoid is not fiber-wise amenable, so so if your G is not fiber-wise amenable, so G is almost elementary, if and only if. So G is purely infinite. Yeah. The pure infiniteness was also introduced first by Matsui, okay, in the ample case, but then I generalized this notion to the higher dimensional setting and show that this notion, okay, indeed also implies that your CC algebra is purely infinite, or even strongly purely infinite. So if you are under some assumption, so like there's only finitely many ideals. Also, the interesting part, so the motivation he introduced is also to study topological four groups. Okay, and we will discuss maybe in the next section. So okay. So then, by using that theorem, so we can also recover something. So like in this case, so you are this one, of course. So we only care about the minimal case in this side. So it's fully infinite. Simple. Or if you want, if you added the amenability, a topological amenability for groupoid, so that is for infinity stable. Yeah. So yeah, so I guess that's the complete story for the for this section. Yeah. Yes.
So when you say non-fiber-wise amenable, that's saying there exists some fiber which is not amenable, or do you actually want all of them to be non-amenable?
Actually, so if the groupoid is minimal, that's equivalent.
Okay.
Yeah. So we call that even stronger, the ubiquitous fiber-wise amenability. Yeah. But that's a very good point, yes, because for the metric space, so because it lacks homogeneity, so it can be some part to be amenable, but the other part is highly non-amenable. So for example, like this one. And you adding a n here, right? So this is just a copy of F2. So this part is highly non-amenable, but on this line it is amenable, right? So the minimality is important here in the groupoid. Yeah.